Contour integration assignment 2. Example. Show that integration from 0 to pi 1 plus 2 cos theta over 5 plus 4 cos theta d theta is equal to 0. In this example, we are having function in the numerator and also in the denominator, right? So there is nothing to worry. We just have to first ensure our limits. The limits are from 0 to pi, so it is needed to be changed, right? And because we are having the cos function in this integration, so we know that whenever we are having the cos in the integration, we know that f of 2 pi minus theta is equal to f of theta. If this rule is applied, because why this is f of theta? Because for cos theta, cos of 2 pi minus theta is always equal to cos theta, right? So whenever cos is present in the integration, you just have to change the limits of the integration because this rule is always applied, right? And because cos of 2 pi minus theta is cos theta always, so we always get our integration path back, which is given to us, right? And if you are having sine of theta instead of cos, then there is a little more change is needed, because sine of 2 pi minus theta is not equal to sine theta, that is equal to minus sine theta. So in that case, you have to convert the sine theta into cos theta format. Okay, fine. So we just have to now put z equal to e the power iota theta, and from there I get d theta is equal to dz over iota z. Fine. Now this integration is equal to, because I need my limits from 0 to 2 pi, and also I know that rule is certainly applied over here always because of cos function. So I am changing these limits to 0 to 2 pi, and whenever we change the limits from 0 pi to 0 to 2 pi, we divide the integration by 2, right? So this is 1 plus 2 cos theta over 5 plus 4 cos theta d theta. Now because we have limits from 0 to 2 pi, it is a complete circle. So now I am going to put z in the polar form and get my function all over in z, in terms of z. So this is equal to 1 over 2, and whenever in the next step, you don't have to write now from 0 to 2 pi, because this integration is now in terms of z, and z is your circle, mod z is equal to 1. This is your circle, so you write c over here, which denotes circle. So this is 1 plus 2, and instead of cos theta, what we are having? 1 by 2 z plus 1 by z. So this is 1 over 2 z plus 1 by z, because cos is equal to this in terms of z. 5 plus 4 by 2 z plus 1 over z, and instead of d theta I am having dz over iota z. Just solve the numerator, solve the denominator, and get your whole expression in terms of z, and that function is f of z. Take whole of this as f of z dz integration, where this f of z will be equal to, if you solve, your function will be 1 over 2 iota z square plus z plus 1 over z into 2z square plus 5z plus 2 when you solve this, you will get your fz as this. And now we have to find the poles of this function. For finding the poles, I have to take this whole denominator is equal to 0. Yes, z is also there in the denominator. So I am taking this whole denominator is equal to 0. And what values of z I am getting? Z is equal to 0. And also from this quadratic polynomial, I get z is equal to minus 1 by 2 minus 2. Now check which are these poles or which of these points lies inside the circle mod z is equal to 1. Take the mod of z equal to 0. Mod of 0 is 0. 0 lies inside the circle. Take the mod of minus 1 by 2, which is 1 by 2. So 1 by 2 lies inside the circle, right? Because its mod is 1 by 2, so it lies this point, z equal to minus 1 by 2 is inside the circle. Yes. And z is equal to minus 2. Take the mod, which is equal to 2. So it is outside the circle, right? So this point minus 2 is outside the circle. I guess it's not here, it should be here because it is negative this side. If you see your number line, this is 0 and circle is mod z is equal to 1. So here it is 1, here it is minus 1, here it is 2 and here it is minus 2. So obviously the point z equal to minus half is inside the circle. And this minus 2 is outside the circle, right? This is your circle, mod z is equal to 1. So now we are having two poles inside the circle. One is z equal to 0 and other is z equal to minus 1 by 2. So now I am going to find the residue of the function at these two poles and then take their sum, because Cauchy residue theorem says that the integration is equal to 2 pi iota times the sum of the residues of fz at all the points inside the circle. So we are having 2 points. We calculate the residue for all these 2 points and taking their sum. Now residue of fz at 0. What is the formula for that? Limit z tends to 0, z minus 0 f of z. So this is equal to limit z tends to 0, z, what is your fz? Write whole of your fz, which is z square plus z plus 1 over 2 iota z into 2z square plus 5z plus 2. Now z is cancelled with this z in the denominator, and then this is equal to limit z tends to 0, z square plus z plus 1 over 2 iota. Now how to find? Now we have to write this quadratic polynomial in factors, right? So for factors, you take this leading coefficient outside the bracket and then you write z minus the first root and z minus the second root. What is the first root? That is z minus, this is minus half and minus 2. So this is z minus minus half is z plus 1 by 2 and this is z plus 2. Fine. Now putting z tends to 0 over here, you get 1 over 2 iota 1 by 2 into 2, which is equal to 1 over 2 iota. This is equal to 1 over, this should be 4 iota. Wait. Yes, one more 2 is there. This 2. 2 into 2 iota. Putting 0 here, I get 1 by 2. Putting 0 here, I get 2. So this is 2 and 2 cancel. This is 1 over 4 iota. So this is the residue of Fz at 0. Now calculating the residue of Fz at minus 1 by 2, which is limit z tends to minus 1 by 2. Z minus 1 by 2 is plus 1 by 2 into f of z. So this is equal to limit z tends to minus 1 by 2, z plus 1 by 2, and your Fz is z square plus z plus 1 over z 2z square plus 5z plus 2. Because I need to cancel this factor, so I have to factorize this again, taking the leading coefficient outside and writing z minus the first root, z minus the second root. The same what we have done in this step. So this is equal to 1 over 2 iota limit z tends to minus 1 by 2 we are having 2 iota in the denominator of the function. So 1 over 2 iota limit z tends to minus 1 by 2, z plus 1 by 2, z square plus z plus 1, taking the leading coefficient outside, so this is 2z into z plus 1 by 2, z plus 2. So z, this is your leading coefficient, taking to outside, this will become 2z, then z minus minus 1 by 2, that is z plus 1 by 2, and z minus minus of 2 is z plus 2. So this factor is cancelled with this factor, right? And now putting the limit z equal to minus half over the numerator and also in the denominator, and you will get this equal to minus 1 over 4 iota. Right. Now sum of the residues of Fz at the points lying inside the circle C. At the first point z equal to 0, I am having the residue 1 over 4 iota. So 1 over 4 iota plus the residue at the second point that lies inside the circle, that is, the residue at the second point is minus 1 by 2, and I get the residue of Fz at minus 1 by 2 as minus 1 over 4 iota. So this is equal to 0. So by Cauchy residue theorem, the integration Fz dz is equal to 2 pi iota times sum of the residues of Fz. So this is 2 pi iota times the sum of the residues is 0. So here it is 0. So this is equal to 0. Hence, the given integral is equal to 0. Fine? Easy? Yes. Next example show that integration from 0 to 2 pi 1 over 5 plus 3 cos theta d theta is equal to pi by 2. Now here limits are from 0 to 2 pi, so there is nothing to change in the limits, right? And also we are having cos theta in this integration, so it's okay for us. So just put z equal to e the power iota theta, and from there d theta is dz over iota z. Thus the given integration is equal to, now because I'm going to change this integration in terms of z, so I have to mention c over here instead of these limits. So this is 1 over 5 plus 3. Cos theta in terms of z is 1 by 2. So this is by 2. Z plus 1 over z. And instead of d theta, I'm having dz over iota z. If you solve this, you will get 2 over iota integral over c 1 over 3z square plus 10z plus 3 dz, and taking whole of this as f of z. Right? Now, the poles of this function fz are given by taking this denominator is equal to 0. So after taking this equal to 0, I will calculate z as, it is minus 1 by 3 and minus 3. Okay, which of these poles lies inside the circle mod z equal to 1? Yes, minus 3, very good. So minus 3 lies inside the circle. Sorry, minus 3 is outside the circle. Sorry. Yes, minus 1 by 3 lies inside the circle and minus 3 lies outside the circle, right? So if you have your circle as mod z is equal to 1, so this minus 3, take the mod which is equal to 3, it lies inside the circle. So you are having, oh my god, I'm so sorry, this lies outside the circle. Minus 3 is over here. And minus 1 by 3 lies inside the circle. I'm very sorry. Okay. Now clearly the pole at z equal to minus 3 lies outside the circle and z equal to minus 1 by 3 lies inside the circle. Now residue of fz at minus 1 by 3, I am having only one pole inside the circle, so only I have to find the residue for this pole. So this is equal to limit z tends to minus 1 by 3 z plus 1 by 3 f of z, because it is z minus 1 by 3, so it will be z plus 1 by 3. So limit z tends to minus 1 by 3 z plus 1 by 3. What is your function? Your function is, yes, 2 over iota 3z square plus 10z plus 3. So this is 2 over iota 3z square plus 10z plus 3. Limit z tends to 1 minus 1 by 3, 2 over iota z plus 1 by 3 over, taking this leading coefficient outside, so this is 3, this is first root z minus 1 by 3 plus 1 by 3, and z minus 3 is z plus 3. This is cancelled with this. And now putting z equal to minus 1 by 3 in this limit, and you will get 1 over 4 iota. So by Cauchy residue theorem, this integration fz dz is equal to 2 pi iota into, yes, residue of fz at z equal to minus 1 by 3, which is just now we have calculated 1 over 4 iota, which is equal to pi by 2. So your complete integration is equal to pi by 2, right? Today there is no exercise for you, right? Alright guys, thank you.